So I would strongly encourage people, I mean, you guys are adults, you can do what you want to do, but I'm going to strongly encourage people to plug in what we're doing today, like full speed. I think if you don't, you're cheating yourself with some opportunities in class to really get this stuff. You know, I wouldn't put it on yourself to try to get all this outside of class. It's too hard, right? I can be flexible with deadlines, but the time we spend in here, I think you got to just really follow along as closely as you can. So here's our function, right? We got to find the derivative of that. Well, what are you going to do? How are you going to turn this into a derivative function? What are some things you like? What's probably the most important point on that function where we know the value of a derivative? Okay, good. I'm seeing people doing this, right? So right there, we see we've got a horizontal tangent. So what does that mean the value of the derivative would be? It's got to be 0, right? Okay, to the left of that, so there's our 0 derivative. To the left of that, what can you tell me about those derivatives? See, they're large negative slopes, less negative, 0. Small negative, big negative. Well, which one fits that? D. Clearly that's D, isn't it? Because there's our 0, and to the left, the further we go to the left of the 0, the more negative it gets, right? The value of the derivative corresponds to the slope of the curve. So up here where we've got this, let's make this a green tangent. So where I've got that steep green tangent, that should correspond to a large negative value on the derivative function, right? Over here where I've got, let's make this purple, where I've got this steep, where I've got this steep negative tangent, so large negative slope, that would correspond to a large negative value on the derivative function, right? No big. So just seeing that relationship is important, though. So there's one. There's our answer. Okay, we got it. Good deal. All right, let's move on. There we go. Okay, what about this one? Same kind of deal. All right, we want to write the derivative of that function. Well, this is broken up into pieces, right? And there, there's obviously going to be some variability in the questions, but they're pretty consistent. I mean, there might be some other slightly different shapes you'd be looking at, but this is, I want to take a piecewise function and break it into a derivative. So what do you know about the piece that goes, let's divide this thing up. So here's a division between, here's a division between pieces, right? And there's a division between pieces. So what about the left of that division? What's the derivative look like?
Negative number.
Yeah, it looks like it's a constant negative slope. It's a line, right, with a constant negative slope. So we know that to the left, if we were going to graph the derivative function, we don't need to worry about what the exact value is, although I guess we know. It looks like it's -2, doesn't it? Right? So we'll go down to -2. We should end up with a line that's a horizontal line, right? The derivative is constant, so the value of the derivative is always -2. What can you tell me about when we get to x equals -2, when there's a break in the function? What does that tell you about the derivative? It doesn't exist, right? Differentiability implies continuity. It has to be continuous to be differentiable, right? It's not continuous, so we'd have to put an open circle there, right? Well, already that's given us a pretty good idea. We could cancel out that one. Well, I guess just that one, right? Okay, so he's gone. What about over here on the right side? Let's look at that one. So the furthest to the right, so everything to the right of the second subdivision, so this part over here. What's the slope? Constant, it looks like -1, right? Now, even the values, I mean, that's not going to be as big a deal, but constant and negative, so this is going to be, and we know we got a break in the function, so we got to have an open circle, then it goes to the right, so that leaves us with that one, and that one is gone, right? So now it's just a matter of which one of those fits the behavior in the middle better. Well, in the middle, we can see that right there we've got a horizontal tangent, so we should have a 0 derivative at x equals 0. Both of those fit the bill, but which of them makes sense in terms of the rest of the function? If I pick a point, let's make it green. If I pick a green point over there, look at that tangent. Positive or negative? Positive, right? Over here, positive. So it's got the value of the derivative is positive to the left and right of that 0. So it has to be this guy, right? Okay. Got it. All right. Okay, so what about this now? This is telling us a couple things. We've got to sketch the graph of f prime of x equals 7x. So we just got to graph the line 7x. Well, you guys have done this more than I have. I'll do that. And then if it's, is it 7x? So how do I graph that?
Hit the line.
Hit the line. I'm going to want to point. We know that positive 7x has a y-intercept of 0 and a slope of 7. So I'm going to rise by 7 and run by 1. So there it is, right? Now what do I do? Save. Okay, there's my derivative function. So which of the following are possible graphs of the original function? If that's the derivative, what function would I have to differentiate to get that derivative? So we're thinking backwards now, right? If the value of the derivative, for example, is 0 right there, the value of the derivative, what does that tell you about the slope of the curve when x is 0? 0. So that means horizontal tangent, right? So it would have to be neither of those two, right? At x equals 0, let me blow that one up. So if we make this one a little bit bigger, that works, doesn't it? Because I've got a horizontal tangent at x equals 0. So does this one, right? It's got a horizontal tangent at x equals 0. They both work. So far, so good. Okay, if the value of the derivative is positive over here, like if I go over to, for example, x equals 1, I get a value of the derivative that's positive 7. What's that tell you about the slope of the tangent line then at x equals 1? Positive 7, right? It's got to be a steep positive tangent line. What about down here? If I go back to x equals -1, the value of the derivative is -7. So the slope of the curve must be -7. Which one is it then? It's got to be D, right? It's got to be D. Because over here at 7, there's our steep positive tangent. Over here at -1, sorry, at 1. At -1, we get our large negative derivative, meaning steep negative tangent, right? So we know it's got to be D. Okay. So what do I have to, oh, is more than one graph possible? Yeah, I mean, in order to get, really all we care about with the derivative is just the shape of the curve, right? That parabola could be clear up here or it could be clear down here. We could vertically offset it. It doesn't change the slopes of the tangent lines, right? So the answer is yes. Okay? Questions so far? Okay, so this is, a lot of this is just, it's just conceptual. There's no calculus to do here other than just knowing the relationships between derivative functions and functions, right? Okay. Same kind of thing here. So this time they're asking us, find the values of x on the open interval where x is greater than -2 and less than 6, at which the function g, which is graphed below, is not continuous and where it's not differentiable. Okay? So where is the function between -2 and 6? Where is that function discontinuous? 4. How come, Daisy? There's a hole, right? Think of my rule. If I'm looking at the graphical rule for continuity, a function is discontinuous where I have to pick my pen off the board, right? Okay, so we know. Right away, we know it's discontinuous at 4, at x equals 4. Okay? Well, before I even think about here, the other places where it's not differentiable, one of them is a freebie, right? Where's one place where it's guaranteed, based on our answer to part A, where's one place where it has to be undifferentiable? 4, because it has to be continuous in order to be differentiable. Differentiability implies continuity, right? So automatically, we know 4 is one of our answers. Okay, are there others though? Where else? Where else? At 2, how come? It's a sharp corner. Okay, sharp corner. So wherever we have a sharp corner, derivatives are undefined also. So we're going to get 4, 2. Okay. Okay, so choose and while we're at it, let's choose the graph of the derivative. Okay, so what are we going to find? If we look at these graphs, we break this thing up into parts, we know that looks like we got a horizontal tangent at 0, right? So we know the value of the derivative has got to be 0 at 0. Well, that's all of them. That doesn't really help us that much. Where else? Okay, so then to the left of that, it's going to be positive. To the right of that, it's going to be negative. Okay, so that crosses out that one, doesn't it? And it crosses out, well, I guess that's it. Okay. What about right here? We know the derivative has to be undefined, so I'm going to have an open circle there, right? So that crosses out that one. And actually, it crosses out that one too, right? So let's just verify here that this one fits the bill. Okay, does it match? 0 tangent. There's our green point. Okay, let's make an orange tangent over there. That's positive. There's our orange positive value for the derivative. We've got a purple negative slope tangent line. There's a purple negative value of the derivative. It's kind of small. You guys see that? We have a break in the function, so there's going to be our open circle, right? Place where the derivative's undefined. And just to the right of that, what are we going to use here? Red, how about? We're going to have another positive tangent, which means it's got to jump up to a positive value of the derivative, right? And then finally, how about pink? So to the right of that horizontal tangent, we're going to get a negative value of the derivative. And notice that we also have to have an open circle in our derivative there because the function's discontinuous, so the derivative also is undefined. And so there's our other open circle, right? You see that? That's pretty small, but you get the idea? Yes?
No, right. Well,
Well, go ahead.
so on A, it has the one line just ends because I'm the open circle on it. Isn't it? Or, it's hard to see.
So it's that I drew or that
No,
is in the original problem? Okay, so should I get rid of all this junk here then? So you're saying, say it again, Kirk.
It has the one line on graph A.
Mm-hmm.
It doesn't have the circle. What would that mean if it doesn't have an open circle line? It's just,
Oh, okay, this I see right here. What happens if I click that thing? Does that make it really big and hold it? Yeah,
Yeah.
so that's gotta be wrong because that's implying there, when you don't see, that's implying that one of those endpoints is defined, right? Because it looks like, they're drawing open circles for places where it's undefined, right? So right away, you know that has to be wrong. Okay, good question. Right, what else? Okay, we good? Okay. So what do we say, this one, right? Okay. Got it? Okay, what about this? Find all values of x for which the function below is differentiable. Okay, so if this is a piecewise function, right? So if we look at this piecewise function, on that piece up there, on the top piece of the piecewise function, x plus 4 quantity squared, That's fine on its own, isn't it? Right? There's no place in that part of the function where I've got to divide by 0, or I'm taking a square root of a negative number, or anything goofy like that. So by itself, it's fine. The middle part of the function, x plus 4, fine, right? Bottom part of the function, 5 minus x quantity squared, fine. The only potential difficulties are going to be where? At the junctions, right? Where the pieces connect, right? If it's possible that it's going to be differentiable, but if there are breaks in the function, if there are discontinuities, then for sure the function's not differentiable, right? The other thing that could happen is we could get a sharp corner. We could get different derivatives from the two sides, right? So let's explore those. So let's look at the junction at -3, right? Because that's where we connect the top curve, the top piece, and the middle piece, right? Okay, so let's just start off by taking limits. What's the limit of our function y as x approaches -3 from the left? What's that equal to? If we approach -3 from the left, that puts us up there, right? Well, I can evaluate that directly. What do I get? 1, right? Just get 1 squared, so I get 1. What's the limit of y as x approaches -3 from the right? That's going to be on that piece, right? As we approach -3 from the right, what's it give us? 1. Okay, so there is no break in the function there, right? They connect smoothly, right? But now we just have to know, are the derivatives the same? Okay? So let's take a look at the derivative function. So here's the original function. Let's calculate the derivative function. What's the derivative of, we're going to have to expand that out, aren't we? Right, so what is x plus 4 squared? So x squared plus 8x plus 16, right? And if I take the derivative of that, what do I get? 2x plus 8? Okay, and that's what we get when x is less than or equal to -3. What about the derivative of the middle part? What's the derivative of x plus 4? 1. Good, so we get derivative of 1 when x is greater than, not just greater than -3, and less than 4. Now, do we get to keep that equal sign? Well, we'll see, right? We only get to keep the equal sign if we get the same values of the derivative as x approaches -3, right? If I get different derivatives from the right and the left, that means it's a sharp corner, right? And then the derivative doesn't exist there, okay? So how are we going to do that? Let's take a limit of y prime. We can do another limit. What's the limit of y prime as x approaches -3 from the left? That's up there. There's my derivative function. As x approaches -3, what value do I get? 2. Everybody see that? Right? I'm getting 2. What's the limit of y prime as x approaches 3 from the right? Well, it's 1, right? It's always 1 on that middle piece. Those derivatives are different. So what's that telling us? It's a sharp corner, right? So is it differentiable there? It's not. As we move towards x equals -3 from the left, the tangent on the left has a value of 2, and the tangent on the right has a value of 1. So sharp corner, so that one's, we know that it's not differentiable at -3. So we can take that off of there, right? It's not defined at -3. So there's one place we can add to our list where it's not differentiable. Let's just keep a tally here. At -3, it's not. Okay, what about at 4? Well, we'd have to just repeat that process, right? So at 4, we'll, need more room. Let's just do this. Okay, so let's see if the function's even continuous. What's the limit of y as x approaches 4 from the left? What's that give us? 8, right? We're on the green piece of the function. We'll evaluate the limit directly. 4 plus 4 is 8. Okay, so down here, we'll make this the red piece, right? What's the limit of y as x approaches 4 from the right? 1. Well, that's an easy one then, right? There's a break in the function, it's discontinuous, so is it differentiable there? Can't be, right? Everybody see that? So then our answer is, we'll add to our, oops. There we go. So we'll add to our tally, it's not differentiable at x equals -3, nor is it differentiable at x equals +4. And so what's our solution? That guy, right? Everywhere except at both of those junctions. Okay? Questions? I mean, there's a lot going on there with that one, right? But the calculus isn't really very hard. It's just it's the concept, right? So to summarize, we got to find A, is there a break in the function? Are the limits of the function, not the derivative, are they different from the left and the right of each of those boundaries? If so, derivative can't exist. If they are the same, like they were at -3, then we got to take the derivative of those pieces and take the limit of the derivative at the junction and see if they're the same also. Okay? Good. Okay, what about this? Here's an E one for you, Joe. What's the derivative of e to the 15th? Zero. How come?
Constant.
E's a constant. That's like saying that's identical to asking, well, identical, but it's equivalent to asking the question. That's equivalent to asking the question, what would be the derivative of pi squared? Pi is just a constant, right? So the derivative of any constant is always 0. It's tricky because it makes it look like it's a power function, but it's not. It's just a constant. So the derivative is, just 0. Okay. Looks like there's a lot going on there, but what do I do if I'm differentiating a polynomial? W is the variable. What's the answer going to be? 12. I'm just going to differentiate term by term, right? The fact that we got multiple terms is no big deal. We're just going to differentiate each one separately. So I'm going to get f prime equals derivative of the first term by the power rule. I just bring the exponent down front, 12w to the 5th, right? What about the next one? Plus 12w squared plus, that's it. Okay? I won't even input it. That's right. Yes. Oh my gosh, okay, so I'm just gonna get it wrong. I don't want to put all that stuff in. Okay, what about this one? Just two terms, I just differentiate term by term. What's the derivative of the first piece? Derivative of 10x? 10. what's the derivative of 9 times cosine x? Yeah, 9 times negative sine x, so we'll just make it negative 9 sine x. Right? No biggie. Okay. No big deal. Only thing that's harder about this is you gotta remember those other trig derivatives, right? So what's the derivative of tangent x? Secant squared. So that one's just gonna be 2 secant squared x. What's the derivative of cotangent x? Good. So negative cosecant squared x done. Okay. And you can enter it just like that. Secant squared x minus cosecant squared x. Okay? Okay, so what about this one? Now, here's where you gotta look at this. This is a little different, right? What's the rule we have to apply here? Gotta apply product rule, because I've got a product of two functions. So let's write down the product rule first. So what's the derivative with respect to x of u times v is what? Well, either way, u prime v, or I can do u v prime, either way, plus, right, either order. Because there's a plus sign, makes no difference, order's unimportant. So on this one, what's my u? My v is e to the x, I'm just following that rule, right? So y prime just equals u, which is x to the 11th, times dv. Well, what's v prime? What's the derivative of e to the x? Yeah, e to the x. Plus e to the x times the derivative of x to the 11th. What's that? I heard it, 11x to the 10th. And then we can just, put the 11 out in front. That's fine. You don't have to do anything fancy. You don't have to factor it. I'm fine with it just like that. So if we enter it, let's just verify, make sure I'm telling you the truth here. So if we enter this as e to the x times x to the 11th plus 11 e, and let's even mess up the order. We'll make it 11 x to the 10th times e to the x. That should be fine. Okay, no problem. Okay, what about this? It's quotients. We've got to use quotient rule. So let's remind ourselves real quick, what's the quotient rule? So what's the quotient rule? This one you got to get right. Maisie, you know this one. What's this one? Oh, don't look. You got it.
Oh, I don't know.
Oh, sure you do. Low to high. So v prime minus high d low minus u v prime over v squared. There you go. Right? So we just got to apply that here. So, Katie, what's my u? That's v, yeah, so 2x minus 5. Okay, good. So y prime then equals v, so that's my 9x plus 4, right? Times u prime, what's u prime? 2. I got to get minus, right? Minus this time, okay? and I get u v prime. So u is 2x minus 5, v prime is 9, all divided by v squared. Well, v is just, now, leave this. You don't need to do anything fancy with this, right? On the bottom, and I'll verify this with my answer, but I'm not really interested in having you expand that out. We'd rather not. We'd rather leave it factored, right? On the top, well, on the top, we do have to clean this up. So we're going to have to distribute the 2, distribute the 9, and collect 5 terms. So we get fewer terms. We really do want to simplify that. So what's that give us? If I distribute the 2, I get 18x plus 8. Let's distribute the minus 9, right? So minus 18x plus 45 all over, oh, let's, I can't, let's go down, got it, over 9x plus 4 squared. So if I can cancel the 18x's, what do I get? 53 over the quantity 9x plus 4 squared. And I really don't want you to have to expand that out. Let's just make sure it works. Should. So 53 divided by the quantity 9x plus 4 squared. Correct. Okay? So you're fine, just like that. Okay? Questions? So far, so good? Okay? Okay, same kind of thing. Quotient rule. You want to do it or not? Okay, skip this one. So I got to get it wrong. I hate getting it wrong. Okay, so what about this guy then? So horizontal tangents of the curve. What we got to interpret that. This isn't a hard question, but we've got to interpret what that means in terms of calculus. Yeah, so horizontal tangents. Let's kind of translate this into English words. Horizontal tangents to the curve. That means that that's where y prime equals 0, right? So we're just, how are we going to solve this thing then?
Find the derivative and then set it equal.
That's it. Find the derivative and set it equal to 0. And the solutions, that's the equation that's going to give us what we want, right? We want to know where, meaning x values, where the derivative has a slope of 0, or the derivative is equal to 0. So what is an easy one to differentiate? It's just a polynomial. Those are a piece of cake. So what's y prime equal to? 3x squared. Okay. Plus 48. And then we're just going to set all that equal to 0. So how do we, and we got a quadratic equation in standard form, take your pick. What are our options? Probably not going to complete the square. That'd be a mess, right? When would you complete the square? So take you back to Algebra 2. When would you complete the square?
You don't have to calculate it, you can just plug in.
Well, okay, sure, okay. But if you had one where you could get it in the form something like x squared plus some even number, like something like x squared plus 8x equals a number, that's a piece of cake to complete the square on, right? If you can get an even coefficient of x, then you don't have to, but I would always complete the square if I had an even coefficient of x. Yep. Question?
Never mind.
Okay. And just quick reminder, that I know it's been a couple of years, but what would that look like, right? That would look like then I know I'm going to get a perfect square is equal to something on this side, right? Well, what goes, just while we're on the subject, what goes there? 4. Yeah, exactly, half of b, right? So I get x plus 4 squared. All I need to know is what number that's equal to, and it's super easy to solve by just square rooting and subtracting 4, right? To find that, what number goes there? I got to add it to both sides, and I didn't even give you a number. Pretend that number was, I don't know, pretend it was -1, right? So we would just end up getting 15 on that side, and we were done, essentially, right? 2 steps and we're done. So that's when completing the square to me is the quickest thing to do. If you can't factor it directly. If you can factor it with easy magic numbers, do that, right? This one, we're obviously not gonna wanna try to, I mean, you could try to factor it. I'll show you a quick trick for trying to get it to factor easily. But what are you probably gonna do on this one? If you don't have a calculator available, which you won't. Quadratic formula, right?
My favorite thing in the world.
There you go. It's probably everybody's favorite thing. So if this is gonna factor, so this would not be a really good one to probably do using factoring, but if you were going to, here's how you could look at this. If it's gonna factor, the only reason you might even try, you'd know that you'd have to have an x and a 3x to multiply to 3x squared. Right, so you know you'd be getting 3x and x, and then you'd have to just see, is there a convenient way? It's really a poor candidate though, because there's like a cajillion factors of 48 that you'd have to try, right? If that were something, instead of 48, what if that were like 23 or something? Then there's only one set of factors. You could just kind of trial and error and see if one of them works, right? But in this case, it really isn't a good candidate because there's so many different ways to make that work. Probably 16 and 3 would be the ones you'd pick. It's 24 and 2. So this one is going to actually probably work. You're going to do, oh no, it's not. It's not. Not going to work. Is it? 16.
Negative 24 and negative.
They both have to be, yeah, they're both going to be negative. It's not even worth trying. I mean, we could wrestle with it, but we're just going to do quadratic formula anyway. So what do we get? X equals, remember it?
26 plus or minus the square root of 26 squared
Okay.
minus 4 times 3 times 48 all over 2a.
There you go. Okay, so 26
Or
squared,
you could do the last one.
that's 625 plus 51, 676.
I'm sorry.
Minus 4 times 3 times 48, so 12 times 48 is going to be 144 times 4, which is 5, is that 576? I think so. All divided by 2a, and so we're going to get 26 plus or minus, what's that square root going to be? 10?
100 actually.
All divided by
Actually, the square root of
6.
100 is 10.
So we're gonna get 36 over 6, which is 6. So either x equals 6 or 16 over 6, which is 8/3.
Yeah.
I mean, I hope I did that right. I don't know. That's a lot of thinking, but I think we got it right. Let's see.
Oh, shoot, I think you're right. I don't even know. Formula.
All right, moment of truth. Little drum roll, please. Oh, we got it. What do you know? Okay, how about that? Okay. I'll leave you. You'll have access to a Desmos calculator too for doing things like quadratic formula. I don't know. That's right.
Like there's no graphing calculator?
No, not on this one. That's coming soon. Not yet though.
And what will we be doing with it once we have?
Well, I mean, just like the computations.
Yeah, the graphing calculator.
Oh, lots. Yeah, you can do most of this test without even thinking on a graphing calculator, which I don't want you doing that yet. I want you thinking right now, but eventually.
Wait, are there shortcuts to getting the derivatives out of the time?
No, you got to take your route.
Is it kind of like when we have?
You can do chunks of this test without having to think an awful lot.
Is it kind of like
Okay,
when
so-
you guys get to see multiplication problems and what to do and how to do?
Oh, I do not have
Well, we'll deal with that later. We'll deal with graphing calculator stuff later. For now, super easy question, right? What's this asking you to do? Differentiate, right? First derivative, second derivative, third derivative, fourth derivative. Do we want to go through it?
Yes.
Okay. So what's y prime? Derivative of the first term.
X to the third.
X to the third. How about this one?
7 over 3?
So I'm gonna get 21 over 9, which reduces to 7 over 3. So we get plus 7/3 x squared
Minus 2x
minus 2x
plus 8.
So there's y prime. How about y double prime?
3x squared
Plus,
14 thirds x
I just bring the 2 down, 2 times 7 thirds, x.
minus 2.
You get the idea. Every
Wait,
every
can we do the
successive
last one?
derivative. Say it again. Sure. So y, do them all. Y triple prime is
6x
plus,
14
It is
thirds.
November.
right? And then finally, what's going to be our fourth derivative?
Oh, I thought it was, I don't know.
Oh yeah, that's, because we just get tired of making the little primes, right? I mean, the 21st derivative would be kind of a pain to write if you didn't
Yeah.
use that little.
Can you imagine derivative 21 times? That'd be, imagine
Yeah.
the original function, it'd be pretty complex.
Yeah. Okay.
Assuming that it's not.
Well, we almost made it. Well, how about we finish up the last two tomorrow, and then I'll give you guys a chance to work and ask individual questions, and then we'll.
I know, they're pretty small.
You
can make them bigger. You still want those last two assignments that, Saturday night.
You don't know what I thought.
No. What did he say?
Try hit that one.
Just already, did you just say hit that whip?
Oh.
I literally said, go hit that whip, and I was like, oh,
I got it.
oh, okay, let's hit that whip. Hit that whip.
I have no idea what that even means. I wouldn't say it.
Show 'em. Hit that
No,
whip.
no, no, don't. I can guess what that means. I don't want to know or see it.
Hey, I just wanted to apologize for my phone. We're getting congressional nomination
Oh,
interviews set up,
You're fine.
so I was kind of like, we have to have them in by 3 o'clock today. So I was had to
sweat.
text my mom.
No sweat.
I wouldn't be on my phone if it wasn't.
No sweat, Kirk. Not a biggie.
Mr. O'Leary,
Yeah.